So in previous lecture, we learned about the implementation of the LUNET. Okay. So is there any questions regarding this? No? Okay. So especially I mentioned this data loader. This is the easy way to load the data in the PyTorch. You don't have to use this, but if you use this, there's some helpful functions. Okay, so I recommend you to use this. And to use that, either you can load the data using this dataset instance. So the popular dataset is already implemented in datasets class, right? So you can load that using the predefined PyTorch function, or you can also define the new dataset class by yourself. Okay. So you have to implement these three methods. Okay, and this is the most important function. Okay, how to define how to load the data should be implemented here. Okay. And we also learned about the difference between SGD and GD, right? So GD, we see all the data, all the training data, and then update the parameters once. And stochastic gradient descent, we only see the partial data. Okay, in theory, GD is more optimal. Okay, but in practice, our data at testing time is different from the training data we use for optimizing parameters. So in practice, GD often tend to overfit to training data. Okay, so in practice, if we train the model using SGD, it performs better than GD for the testing data. Okay, so this kind of randomness is helpful when the training and testing data are far different. Okay. And this is the code for implementing the training and testing code for training the CNN architecture, such as LUNET. Okay, this is the early CNN architecture. Okay, so you can feel that most of the methods we use here are similar to what we have done for training the linear regressor or the MLPs. Okay, there is no far difference. Okay, and this is also useful when you conduct the programming assignment or your final project. So you have to use GPUs to accelerate your training. Okay. And in Colab, it is easy, right? You can just set GPU from your menu, right? But when you try to use your GPUs in your local machine, you have to properly install the CUDA, okay? And you have to copy your data and also have to copy your model into the GPU, okay? Then the training time will be reduced, okay? And then we will see the intuition for more recent CNN architectures. So as I explained, in this graph, here in the year of 2012, the AlexNet appears, right? This was the first architecture that records the state-of-the-art accuracy in the ImageNet dataset, which is the largest image classification dataset. And then the more deep architectures were introduced, such as the VGG network and the Google LUNET architecture and the ResNet architecture. Okay, so I will introduce brief motivations of them. Okay. So AlexNet was the first successful architecture that records the best accuracy in large-scale data sets, such as the ImageNet challenge. So their architecture is quite similar to LUNET, okay? Mostly it is composed of the convolutional layers, and also it involves some non-linear layers, and also had some pooling layers, right? But I mean, the first difference is for the non-linear layer, they are using the ReLU. Previously, when you implement the LUNET architecture, in their architecture, you can see the nonlinear functions are tangent hyperbolic, okay? But tangent hyperbolic is not having proper gradient. The tangent hyperbolic graph looks like this. So we have to delete. So all the x values minus infinity to infinity, the x values are spanning from minus infinity to plus infinity, but their y values are bounded to -1 to 1. That's tangent hyperbolic function. Okay, but the gradient in here, when the x is large, when the axis becomes larger or smaller, the gradient in these regions are almost goes to 0. And because of the precision issue, sometimes the gradient simply goes to 0, okay? And this makes the overall gradient goes to 0, and this can make some problem, okay? So apart from this tangent hyperbolic, the sigmoid function have the similar issue, right? But when we use the ReLU function, which looks like this, which is have the y is equal to x graph when the x is positive, and when the x is negative, it is outputting simply 0, okay? Here, there's no issue like that, okay? There's no issue for reducing the scale of the gradient, okay? So in here, AlexNet, they are proposed to use the ReLU instead of other nonlinear functions, okay? And also, these two are kind of very practical issues. So to accelerate the training speed, they involve to use the multi-GPUs, okay? So GPU have the multiple cores inside, so it can calculate simple operations parallel in the parallel way. So we can accelerate our training. So because of that, we can use large scale data sets, okay? Unless using the GPUs, maybe it takes like a month to training the AlexNet-like architecture using CPU, but using the GPU, we can accelerate the training, okay? And also, this dropout is also important module, but here, maybe we will skip this layer, okay? So, but I think you can review this dropout layer by yourself. This is roughly proposed to giving some randomness, okay? So because the training and testing data set are different, overly fit to training data during the training stage is not helpful for obtaining good accuracy in testing, right? So giving some randomness during the training stage is helpful, and this dropout is proposed in that sense, okay? And also data augmentation, this is for augmenting the data, okay? So, I mean, ImageNet, it is the large-scale data set, but giving more data, it is helpful for recording the good accuracy. So this kind of data augmentation is proposed, okay? So because thanks to these three schemes, AlexNet has recorded state-of-the-art accuracy in ImageNet challenge. Okay. And this is the implementation of the AlexNet using the PyTorch code. Okay, so this is the AlexNet class, and you have to define the init and the forward. Okay, and init you will define the structure of the main network. Okay, and this is composed of three parts. The first part is convolutional layer, composed of the 2D convolution and nonlinear and pooling method. Okay, and here we define the average pooling, right? And then at the last FC layer, we define the fully connected layers using the 1D operation, using the linear operation, okay? And then in forward method, we first apply the feature, the convolutional layer, and then applying the average pooling to reduce the 2D dimension, and eventually flattening it and apply the FC layer afterwards, okay? This is the AlexNet. It's quite similar to the implementation of LUNet, but having different nonlinear function, okay? And have some more layers, okay? This is having mostly 8 layers, okay? So slightly deeper architecture having different nonlinear functions, okay? We can simply implement this AlexNet using PyTorch, okay? And also in BridgeNet, the motivation here is like this. So here you can see the first architecture, deep architecture that records the state-of-the-art performance in ImageNet was having the 8 layers. But here, the BridgeG and Google LUNet appeared in 2014, having around 20 layers, okay? And the ResNet, it has more than 100 layers, okay? So the layers are getting deeper, right? So in general, we can say in deep learning, when we involve more layers, the deeper layers, the performance of the deep architecture becomes better, okay? So the motivation here for BridgeG network and also the Google LUNet architecture is stacking more layers, okay? So BridgeNet, it has several models, several baseline models, and it has 11 layers to 19 layers, okay? Anyways, it has more layers, the AlexNet, which have only 8 layers, okay? So BridgeNet, they try to investigate the relationship between the depth of the network and the overall accuracy, okay? And also they mostly compose their architecture using 3x3 convolutional layer, okay? So this is the BridgeG network. So AlexNet was successful, right? It records 10% accuracy improvement in ImageNet challenge. Okay, and BridgeNet, they are experimenting the relationship between depth and the overall accuracy. Okay, and have made several in-between architectures that improves the stacking more layers to till 19 layers. Okay, this is the AlexNet having only 8 layers, and this is the one of the BridgeG network having 16 layers. Okay. So here you can see they are stacking more convolutional layers having 3x3 filter kernel, okay? And this green is denoting the FC layer, okay? So this is the definition of the BridgeG 16 architecture having 16 layers inside, okay? So in here, in the init method, you can see they are defining some basic blocks, okay? And mostly they are having convolution, 2D convolution operation having 3x3 kernels, okay, you can see they are mostly defining the blocks having 3 by 3 filter kernel, okay? So they are making 5 types of blocks, okay? And then here, they also define the FC layer at the last part. And then in the forward function, they implement it like this. First, feeding your input via these 5 types of blocks, having the 3 by 3 convolutional layer, and then flatten it and apply the FC layer at the last, okay? So this is the definition of the bridge network, okay? So this is easy, right? Okay, and also here, so the lesson is if you stack more layers, the accuracy is gradually getting better, okay? And another important architecture is Google Net. So initially their name was Google Net, but so some guys, some authors are saying that they are inheriting some philosophy from the LUNet architecture. So sometimes people are calling that as Google LUNet, okay? And in their architecture, the basic block is this kind of inception module, okay? This is their basic modules. So in normal CNN architecture like LUNet, AlexNet, or VGC network, their basic block was just the convolutional layers and FC layers. But in Google Net, their basic block is inception module. But this is not that different from previous, but having some special features because this is the previous layer's output. And in parallel way, you feed your previous layer's output to 4 modules, the 1 by 1 convolution, 3 by 3 convolution, 5 by 5 convolution, and 3 by 3 max split, okay? And then you will concatenate all the responses. And that's the response of this inception module, okay? So, and then in Google LUNet, you will stack multiple inception modules inside. That's the Google LUNet, okay? So here, in the definition of when defining the Google LUNet, you have to define inception module first, okay? And in the init method, you have to define 4 different operation, okay? The 1 by 1, 3 by 3, 5 by 5 convolutions, and also the max splitting. And then in the forward function, you will apply these 4 operations in parallel way. And then you will concatenate them and will return them, okay? This is the inception module, right? And then in the Google LUNet architecture, using the first layer would be just composed of the convolutional layer and also the max splitting layer, right? But from the second layer, your basic block would be inception module, right? So some sub modules that is based on the inception modules are defined. And in the forward function, you can define the forward function like this, okay? So this is the Google LUNet architecture having 22 layers, okay? So this is also easy, right? So this actually surpasses the accuracy of the VGC network, okay? But one important, so roughly, as you see in this graph, if you stack more layers, the accuracy becomes better, okay? So we can conclude that like, if you stack more layers in the deep learning, the accuracy would become better. That was the general conclusion. But one thing is, when we stack, at the time of bridge network, if we stack more than 20 layers, then some strange things happened. So, I mean, here, maybe this is the A layer result. Okay, this is the testing and training error. So let's say this is the A layer result. So if you have the deep learning architecture having just 8 layers, their training error and also the testing error would be higher than the network having 20 layers. Okay, if we stack more and more layers until we stack around 20 layers, the training and testing error would be smaller, right? So if the error becomes smaller, it means the network is performing better, right? So if we stack more layers, it performs better than before. But after 20 layers, if you stack more layers, then the strange phenomenon occurs. So if you stack more than 20 layers, the testing error and also the training error, they are becoming worse, okay? So this is because of the vanishing gradient phenomenon. So there are many causes for the vanishing gradient effect, right? So, but this is another aspect that causes this vanishing gradient. So, as I mentioned to you previously, if we stack only 20 layers, we have to calculate loss. The final layers output would be loss. And maybe let's say this first layer's parameter would be sector, but we have to calculate DLD sector properly, right? But and also this gradient would be defined step-by-step manner, right? So like this is Y1, let's say. So I mean, this gradient could be via the chain rule could be defined like this, right? Each layer's gradient could be multiplied together to get the final output gradient respect to the earlier layers parameters. Okay. But one thing is, if you have terms larger than 20, if you multiply the gradient values, which is normally less than 1, multiple times, and more than maybe 20 times, then these values simply goes to 0. Because of the precision issue, the PC computer cannot represent the values, which is very small, right? So it's simply represented as 0, right? So because of this issue, if you stack more and more layers, the gradient value, which is small, simply goes to 0, and the training cannot be performed properly, okay? So that's why this happens. So until 20 layers, these values are small, but the computer can represent that still. But if you have more and more layers, this value simply goes to 0, and you cannot represent proper gradient, which is essential for the training, okay? So the training cannot be done properly. So this idea of resonance is, some of you already know that this is the normal architecture, and this is the resonant architecture having some residual connections. So this is the plane layers having convolutions, sequence of the convolutions, right? This is the input and this is the output. And you have some convolutional layers in between the input and output, okay? This is the plain layer. But in the residual block, apart from the original sequential convolutions, you have this kind of another path, okay? So your original input would be applied to this route and will be added to the original output, okay? So let's say this is called as, let's say this is f function, and previously your output would be just applying function f on your input x, okay? But in the residual path, your output would become like this, okay? And if you calculate the gradient for this and this module, then you will see why this residual connection is helpful for reducing the vanishing gradient. So if you differentiate your final output h respect to the input x, then that would be this, okay? And normally it is less than 1, okay? And normally it's positive, okay? If you multiply this small scale value multiple times, then maybe after 20 layers, this value would be go to 0, okay? But if you differentiate this function respect to x, then it would be like this, right? Then these values are same as this and could be bounded to 0 and 1. But because you added the original input x to the output signal, you will, your final output, your gradient would be around 1, right? Because you added original signal and differentiate, you will differentiate your new output respect to x, then you will have this constant 1, right? And this will guarantee your output, your gradient scale, right? To be around 1, okay? So now if you multiply this gradient multiple times, your gradient may be not converged to 0 easily, right? So are you guys following this? So because of this, in ResNet, we can prevent the vanishing gradient, okay? So previously, without this residual connection, we cannot easily stack more than 20 layers. But if you use this residual connection, we can stack more than 20 layers. And in ResNet, we have like ResNet 30, 34, and ResNet 50, and also ResNet 101 and ResNet 152. Okay, so these are indicating the layers stacked. Okay, so that's why in ResNet, we can stack more than 20 layers because thanks to this residual connection. Okay, and also this is the implementation of the ResNet in PyTorch. Okay, so first, we have to define multiple convolutional layers, okay? So for some convolutional layer, it would have some stride, okay? And so on. So depending on the hyperparameters, we define multiple convolutional layers here. And also we have to define the bottleneck block, okay? And actually we define 3 types of bottleneck modules, but they are mostly having different hyperparameters, and sometimes we have to adjust their dimensions, the output dimensions, by resizing the output. So that's why we have different bottleneck modules. So this is having some stride, and this is without rescaling. Okay. So here we have to downsample the output signal, but this module, it doesn't have it. Anyways, let's ignore this kind of details, but more important thing is in bottleneck operation, what they do is the thing we have seen in this figure. So this kind of residual connection is defined in these bottleneck blocks. Okay, so when you see the forward function, anyways, this kind of original path having several convolutional layers are defined. So you first calculate the response from those original paths, and then you will add your original signal X to that and return it. Okay. This is the simple implementation of residual block, the bottleneck, the core block of the resonance. Okay. So, I mean, this kind of module, when implementing this may involve some complex gradient calculation. So sometimes this is implementing this without the PyTorch library is, I mean, not very simple, but if you use this PyTorch library, you can just define the forward path by this manner, and the other gradient calculation things would be managed by the PyTorch. So the implementation becomes very easy. Okay. So this is the three bottlenecks having slightly different rescaling and also the stride. Okay. And then in the resonance, the main pipeline, we define also the several modules that is based on the convolutional layer and also based on the bottleneck layers. Okay. And in the forward function, the thing you have to do is just taking this network. Okay. So this kind of things are implemented in this way. Okay. Are you guys following this? Okay. So this is the resonance. So any CNN architecture can be implemented using this kind of class definition. Okay. So I want you to feel that. Okay. So this is the review on the deep learning and PyTorch. And now we will convert to another theme. Okay, so now we reviewed the deep learning and PyTorch. Okay, so now you can feel like that you can implement any deep architectures by yourself, and you can train them using any kind of data, right? Okay. Then from now on, we will expand our knowledge towards the more complex computer vision applications like object detection and semantic segmentation and pose estimation. Okay. So as I mentioned earlier, the object detection task is like this. So the image classification is assuming two strong assumptions, assuming that the images are having just one object inside, right? So the computer vision researchers are not liking that. So they define new task, which is called as object detection. And in their task, they have to define each object's bounding boxes. And at the same time, they have to predict the probability for each category, object categories. Okay. which might be contained in the bounding boxes. Okay, so in this way, we can tackle multiple the images having multiple objects inside. Okay. And also, this is semantic segmentation, and we will tackle this maybe a few lectures later. And so, object detection is different from the classical image classification task. Okay, but maybe in classical machine learning, this object detection is not that different from the image classification, because the researchers are tackling this object detection task in this way. So from the one image, for achieving the object detection, what they have done is using this kind of multi-scale window, they apply these windows in this way. Okay, so this is called as sliding window approach. So they slide each window by few pixels from the left top locations towards the right bottom locations. And for each cropped images obtained, they apply image classification. Okay. So are you guys following this? So using this simple method, object detection could be achieved. Okay. But the problem is it's too slow, right? So let's say we have these dimensional images, then the bounding boxes we will get would be this number, maybe, right? Around this number. And also the shape of the bounding box, it have to be diverse, because maybe if you detect humans, try to detect humans, the humans are having this type of bounding boxes, right? But sometimes the car would have this type of bounding boxes, okay? So you have to use multi-scale bounding boxes for detecting objects. So the window boxes you will have would be number of bounding boxes, types of bounding boxes. This is too many, right? So if you achieve the object detection in this way, considering the multi-scales, the overall computational cost is too high, okay? But thing is, in maybe before the deep learning, we actually does this for detecting the objects. So for example, this is the algorithm proposed by Viola and Jones for detecting the faces, okay? This is published in CBPR 2001. And this type of bounding boxes are applied in the sliding window method. And the thing you will do is you will extract this type of hand-engineered feature from each cropped bounding boxes and will apply some shallow classifier whose name is boosting algorithm. Okay, and you will classify each box towards face or non-face. Okay, this was the binary classifier, and for each detected bounding boxes, you will classify them to these binary classes. Okay, this was the method proposed in this old method. Okay, but thing is, this algorithm is already implemented in the OpenCV, and if you try to run them, their inference time is less than few seconds. Okay, even though the bounding boxes generated is high in volumes, but the boosting algorithm is very fast algorithm. So in classical machine learning, domain, such big numbers are not that problem, was not an issue, okay? Because the algorithm itself is very fast. So applying that in, million times would not be that issue, okay? So the inference time was in few seconds. No one. Okay. So this is the figure for representing the algorithm I mentioned. So this is the region within sliding window, right? And this is denoting the boosting algorithm, which is very fast. And they are classifying the regions, the features of the region into the phase or non-phase, okay? And this is denoting the hard-like features, which is hand engineered, okay? So this was the phase detection algorithm, which uses the this kind of sliding window approach. But the problem is the deep learning architectures is having a lot of parameters inside, right? So even for one forward pass, it had to use the GPUs, okay, to run in the few seconds, right? So the idea first used for achieving the object detection using the deep learning architecture was reducing the number of boxes, bounding boxes. This was the initial idea to achieve the object detection using the deep learning architecture. Okay, unless we cannot achieve the object detection using the deep learning in few seconds, right? It may take maybe few hours, right? Okay, so that is not practical. So people think about new approaches to achieve the object detection using the deep learning. And the initial idea was reducing the number of bounding boxes. Okay, so previously we need this amount of bounding boxes. This is number of multi-scale bounding boxes, right? And this is the width and height of the image. We need this large amount of bounding boxes from an image. But the idea is, if we can reduce this amount of bounding boxes into just 1,000 regions, 1,000 to 2,000 regions, it might be making the algorithm more practical, right? So this might be the number like this. If this is 10, then this is very huge number, right? But this 2,000 is still large, but it's maybe a few hundreds faster than this, right? If we can reduce the number of bounding boxes, right, it can accelerate our inference speed a lot. Okay. So we will call this method, which can reduce the number of bounding boxes, as the selective search algorithm. So from the images, instead of applying sliding window method, we can maybe propose some algorithm that can selectively search the bounding box, which may have objects inside. Okay. So that's the idea of this object proposal. So this object proposal is meaning that let's find some bounding boxes which might have objects inside. Okay. So by applying this algorithm, we can reduce the number of bounding boxes. Okay. And their idea is if there exists an object inside bounding boxes, the color and texture and etc., those hand-engineered features would be coherent in such regions, right? So if there is some regions which may have objects inside, their region's color and textures and other features would be coherent, right? If there is object, okay? So this is assumption, right? Of course, this is kind of assumption, but I mean, this could be some realistic assumption, right? So what they have done is they cluster original image, for example, in color space, and make this kind of clustering map. Okay, the color here is not that important, but the important thing here is if they exhibit the same color, they are, I mean, meaning that those pixels are belonging to the same class, okay, because their colors are similar. Okay? So these color clusters are meaning that same colors are having they are belonging to the same cluster because they are having similar colors. Okay, so we can apply k-means algorithm or a Gaussian mixture algorithm to obtain this kind of map, clustering map, right? So using the clustering algorithm and using the each pixel's color as the feature, we can obtain this kind of clustering map easily. And also using different hyperparameters, okay? Maybe the pixel values are having this kind of scale, right? But maybe the similarity of color, that could be subjective, okay? If pixel values are around, I mean, let's say some pixels are having this pixel value and some pixels are having this value and some pixels are having this value. So we can say these two pixels are having similar color value and these two are distant. But if there's another pixels having this large value, then we can say this pixel and these pixels are maybe having small different distance relative to these two distance, right? So anyway, the color difference, the similarity of color, this is subjective. So this another clustering map is obtained for tackling this kind of subjectivity of the similarity. So this is the clustering map, which is roughly clustered. So, but here I mean, we tightly calculate the clustering map, right? So the same white regions here are clustered together in here, but this is also divided into multiple regions if we tightly cluster images. Okay. So anyway, we can cluster the original images based on multiple features, which is hand engineered, and also with the multiple hyperparameters. So then what we do here is these kind of regions mostly having the pixels which are belonging to the same class in multiple times have the high probability to have an object inside. Okay, So what we do is we obtain this kind of cluster maps multiple times using multiple features and multiple hyperparameters. And then we are using the heuristics. We make the bounding boxes afterwards. So, I mean, this is the algorithm for obtaining these object proposals, which may have the objects inside. So we first calculate the initial regions used by applying the clustering algorithm. And the thing we do is we somehow merge the regions, okay, based on their similarity, okay. Okay. And so this is kind of some algorithm to merge the regions. And then after we obtain the final regions, we can extract the bounding boxes which surpasses this region. So when the final regions are obtained like this, we can just make the bounding boxes that surpasses these regions, okay? And this becomes our final, I mean, the object proposal, okay? And this algorithm, object proposal algorithm, there are several object proposal obtaining algorithms, but the selective search algorithm, this is one of the maybe frequently used one. And this is already implemented in the OpenCV. So this is the examples. If you run this selective search on some image, okay? So instead of obtaining the sliding windows, you can obtain some bounding boxes around the objects, okay? So this is because around these regions, the features are coherent, okay? So this is object proposal algorithm. And maybe, so maybe I will re-explain this part maybe in the video lecture, okay? Anyways. Okay, and also in RSCNN algorithm, which is the first, the CNN architecture that uses this object proposal algorithm to achieve the object detection algorithm. So this algorithm is proposed in CVPR 2013, and this R is representing the regional thing. So regional CNN. Okay. So their algorithm is quite simple. So given the input image, what they do is by applying the selective search algorithm, which may generate around 1,000 to 2,000 bounding boxes. So these boxes are windows you obtain from the selective search algorithm, okay? And for each region, you can apply the pre-trained convolutional layers, okay? So if you resize this region into the, to feed it to the CNN's input, and if you feed this to the CNN architecture, the final output maybe would be the probability or the feature, okay? And so, but here, what authors exactly do is they obtain some features at the last layer, and they involve another shallow learning classifier, whose name is SVM, and train this SVM again to classify the CNN features into classes again, okay? Anyways, what they have done is they apply the selective search algorithm on the initial image, and obtain multiple bounding boxes from an image and apply CNN multiple times for each regions, right? There would be this number of regions, okay? But it is far less than this number of bounding boxes, right? Which might be obtained in the sliding window approach, okay? So this is the thing achieved in this RCNN algorithm, okay? But their limitation is, as you see, they are still slow because they are having still many number of bounding boxes, around 1,000 to 2,000. And also, the other important problem is they are not end-to-end trainable. So this is more important. Maybe at this time, you may not understand this fully, but if you see another algorithm which is more advanced, then you might be able to understand this properly, okay? So now this type of algorithm is actually, but actually if, let's say there is humans like this, right? And let's say you are detecting bounding boxes like this, and you are enforcing this input to computer to recognize which objects are inside here, right? But sometimes it is even hard to recognize this part, which looks like this, for humans, right? We humans also need some context to recognize this part properly, okay? But I mean, in CNN, they are inputting only this patch and have to classify this patch. So the accuracy might be limited in that sense, okay? They cannot get some context around the patches, okay? So that's related to this word. This is not end-to-end trainable, I mean, respect to the overall images, okay? But they get only the small cropped regions as the input. So that's the limitation of this RCNN algorithm. So in ICCB 15, which is maybe the 2 years later, this fast RCNN algorithm is proposed, and they made this differentiable, end-to-end differentiable. Okay, so they start from the original image and then make some initial response and then map it to some multiple regions like this. Okay, so for this part, I will continue in the video lecture. Okay, so maybe the video lecture will be provided to you tomorrow night. Okay, and okay. So today, let's finish here. Okay.